All right, so again, we've got sections 3.4, 3.5, and 3.6. We had a quiz over derivatives. Was that last week? That seems like a long time. Wow. That was a long. That seems like a long time ago. So we had a quiz over derivatives just a little bit ago, and then we're doing sections 3.4, 3.5, and 3.6, and then we will have a quiz, and then we will do sections 3.7. I think it kind of skips around in the chapter. I know we do section 3.11. But then after that, we're almost time for our exam. Okay, so we're going to spend a good amount of time going through sections 3.4, 3.5, 3.6, quizzing 3.7, 3.8, and so on, and then chapter 10. Hold on, I need to see your regular quiz.
I don't know where I put it. Let me go look.
Okay. Yeah, I need to see it. So we have section 3.5 here. It's called implicit differentiation. Implicit differentiation. Remember, all of chapter 3, by the end of chapter 3, we should be able to find the derivative of anything we are given, right? Find the derivative of anything we are given. It could be trigonometric. It could be two functions multiplied to one another. It could be two functions divided by one another. It could be a function within another function. That would be the chain rule, right? So we should be able to find the derivative of anything that we would want to. Even functions that look like this. Oh, I'm sorry, like this. Excuse me. X squared plus y squared is equal to 25. I like the way the book puts this. The functions that we have met so far, like, hi, nice to meet you. Hi, Mr. Function. The functions that we have met so far can be described by expressing one variable explicitly in terms of another, okay? Because there's a difference between explicitly defined functions and implicitly defined functions. Explicitly defined functions are ones that you can write as y is equal to, right? Y is equal to mx plus b, y is equal to 2x plus 4. That is an explicitly defined function, where y is explicitly defined in terms of x, and only x, right? I don't have any other y's on the other side of the equation. I don't have anything else on the other side of the equation other than just an x variable. Or like y is equal to the square root of x to the third plus 1, or y is equal to x sine x. Those we could all find the derivative of by now. But what we haven't really encountered yet are these types of functions. X squared plus y squared is equal to 25. Can anybody tell me what type of function that is? What type of graph does that come out to be? Does anybody remember? X squared plus y squared is equal to 25. Who did you guys have for honors geometry? Oh, I should go. She's not even going right now. She would yell at them for not knowing this. Anybody know what equation that is? That's the equation of a circle. That is the equation of a circle that I guarantee you guys learned way back when. X squared plus y squared is equal to 25. Any circle can be defined as like x minus h squared plus y minus k squared, where h and k is the center of the circle. So in this case, the center of the circle would be 0, 0, because it's just x squared, y squared. And then is equal to the radius squared. So the radius of this circle is 5. Now, this is not even a function, is it? If it's a circle with radius 5, centered at the origin, that's not even a function. That does not even pass the vertical line test, okay? So calling it a function is not really using the correct notation there. It's not even a function, so how do we even find the derivative of it? Like if I go to find the derivative of this, I would have to maybe solve it for y and then try to find the derivative. But in that case, it would really kind of look a little weird. I think it has it down below here. I would have to have it in two separate pieces. Like take a look here. I would have to have the top half and then the bottom half, because if I solved for y, I would get the positive root of 25 minus x squared or the negative root of 25 minus x squared, and then I would have to find the derivative of both of them, and then that gets a little weird. So there's got to be another way. Or another one that we will work with today is this x to the third plus y to the third is equal to 6xy. That's got a fancy name to it, but we'll look at that a little bit later on. But what am I talking about here? I'm talking about functions that have x's and y's in them is part of the equation, okay? As part of the equation, it's got x's and y's within the equation. Now, what we do here is those are called implicit functions. So when we when we have to find the derivative, or when we have to differentiate, we have to use this technique called implicit differentiation. Implicit differentiation. Okay? We can use implicit differentiation here. It consists of differentiating both sides of the equation with respect to x, and then solving the resulting equation with respect to y prime. Now, every equation that we have found the derivative of up until right now has been find the derivative with respect to x. Because we've had this notation d over dx, right? This Leibniz notation says find the derivative with respect to x. Okay? You could find the derivative with respect to other variables. You could find d over dy, and then find the derivative with respect to y. You could find d over dt. You know, maybe we're working with speed and time and our position and time and speed and velocity, acceleration. We find d over dt. That's the derivative with respect to t, with respect to time. This is the derivative with respect to x. And that's all we've done really so far. So what we're going to do now is do that same process, but now we're going to do it on y. Okay. Did you find it? Okay. Okay, so let's find the derivative of this thing. X squared plus y squared is equal to 25. X squared plus y squared is equal to 25. So as I mentioned above, how we find the derivative of this thing is taking the derivative of both sides and then resolving that equation for y prime. Okay? Find the derivative of both sides and then resolve that equation for both sides. Okay, let's find the derivative of both sides. Now, in this Leibniz notation, it's going to look like this. D over dx of x squared plus y squared is equal to d over dx of 25. Because essentially, d over dx is an operation, right? Just like multiplication, just like addition, just like subtraction. Differentiation is an operation that we just perform to both sides of the equation. Whatever we do to one side, we got to do to the other. Now, we have to do it with respect to the same variable on both sides. The right side of this is rather easy. What is the derivative of just 25? 0. Remember, the derivative of a constant is 0. Okay? Now, I find the derivative of x squared y squared, which is essentially just distributing the derivative, right? So that would be 2x. So derivative of x squared is 2x. Now, here comes the funky part. Whenever you go to find the derivative of a y term, and there's something acting on it, like this isn't just finding d over dx of y, right? This is finding d over dx of y squared. There is something acting on the y. Whenever there is something acting on the y, what you have to do is think of it like a chain rule. You have to treat it like a chain rule. Here's what I mean. I am going to find the derivative of the squared. What is the derivative of the squared? 2 times that thing. Right? 2y to the first. And then I have to find the derivative of y. Well, the derivative of y we can treat just as y prime. I know it's really funky. But what we have to do is treat y as like its own separate function. Because really, that's what it is. If I resolve this equation for y, it would give me a whole new function, right? So when we go to differentiate a y, we have to treat it like its own function. So if there's something acting on another function, I have to treat it like a chain rule. If there's a squared acting on that y, I have to treat it like a chain rule. Bring the 2y out in front and then multiply by the derivative of the inside. Well, what is the inside? It's just y in this case. So it just multiplies back on y prime. Okay? Now, implicit differentiation says, just solve this for y prime, and you found your derivative. So I'm going to subtract the 2x to both sides, and that's going to give me 2y prime is equal to negative 2x. If I divide this 2 over to the other side, it makes the 2 on the other side go away. So it's y prime is equal to negative x, excuse me. And then I divide by the y over to the other side. So y prime is equal to negative x over y. That's the derivative. Yes, implicit differentiation will cause another implicit function when you find your derivative. What does that mean? That means when I go to find my derivative, there will be a y value in there. Hi, Emily. Dominic, you're just finishing your. Yeah. No, I'll put you missing that pulses from. You have your original.
Yeah.
Okay. Yeah, just go right at this. I need to see the original to figure out which one. Oh, please. Okay. So, part B of this says, find the equation of the tangent to the circle. Okay? Find the equation of the tangent to the circle. So what we're essentially doing here is saying, okay, if we've got our coordinate plane centered at 0, 0 with a radius of 5, there we go, it's good enough. I have this circle, and at 3, 4, at point 3, 4, there is a coordinate out there, and I am finding the tangent line to that circle. Now, whenever you go to find the tangent line, you need a slope. It gives you the point, but you need the slope. Remember that the slope is equivalent to the derivative, right? The derivative is the slope. So y prime that I had from my part A is negative x over y. Well, fortunate enough for us, we have an x and a y pair. So that means we have negative 3/4 as our slope. Okay, I boxed that, but that's just my slope that I'm going to use to create my line. Negative 3/4. So that means I have y minus 4 is equal to x minus 3. And why not? Let's solve it for y real quick. Distribute in the negative 3/4. Y minus 4 is equal to negative 3/4. X, negative times a negative is a positive. 3/4 of 3, 9/4. What's 9 divided by 4? 2 1/4. Plus 4. Y is equal to negative 3/4 x plus 6 1/4. Okay. Questions about that? Which makes sense, like looking back up at my graph, look at my negative sloping line. Looks like it's a pretty shallow slope, 3/4, and y-intercept probably somewhere above the top value of 5, so 6 1/4. Yeah, it seems right. So you should always go back and double check that. Let's do that process again. So this is the other one that I introduced here at the beginning of the lesson today. The x to the third plus y to the third is equal to 6xy. This has a unique name. It's called the folium of Descartes. The folium of Descartes. X to the third plus y to the third is equal to 6xy. Let me bring up Desmos so you can actually see what this thing looks like. Desmos. Again, it was x to the third plus y to the third is equal to 6xy. Graphing calculator. X to the third plus y to the third is equal to 6xy. Yeah, pretty cool, right? Yeah, it has like a curve up and around to it. Notice that, is this a function? No, it doesn't pass the vertical line test. It doesn't pass the vertical line test. What's cool about this is that it's got two asymptotes to it. There's a like this curves down and it hits at 0, 0, and then it actually comes back up and around and curves right back to 0, 0 again. Right? The point 0, 0 is actually a tangent point at two different spots. Kind of cool. All right, but this is what this thing looks like. This is this implicitly defined function. So let's find the derivative so that we could calculate at any given point on that curve what the slope would be. Okay, so part A says find the derivative. So x to the third, y to the third, plus y to the third is equal to 6xy. Now, this function is not as easy to differentiate because I don't just have a number on the other side. So I want to find d over dx of x to the third plus y to the third, and d over dx of 6xy. You're going to see me write that step in because I think it's really important to remind ourselves every single time that what you're doing is an operation to both sides of the equation. The operation is finding the derivative to differentiate, and I'm doing it to both sides of the equation. Now, when I go to differentiate the left side, let's just go left to right on this one. When I go to differentiate the left side, okay, my first term is quite easy, 3x squared. Now my second term, okay, when I go to differentiate a y value, and there's something acting on it. When I go to differentiate a y value and there's something acting on it, I have to treat it like a chain rule. So this becomes differentiate to the third, which is 3y squared, right? Differentiate the fact that it's to the third, keeping the inside function the same, right? That's the chain rule. And then multiply by the derivative of the inside piece. Well, the inside function is just y, so I have to multiply by y prime. That's the weird part about implicit differentiation. When you go to differentiate the y value, you have to treat it like a chain rule. Okay, now, what do I have to do on the other side here? Not chain rule this time. Product rule, because it's x times y, isn't it? Okay, so remember, product rule is f prime g plus g prime f. Now, my f and my g are just x and y in this case. Okay? You can bring the 6 all the way out in front, or you could keep it with each term. It really doesn't matter. I'm gonna keep it with each term. So when I go to differentiate here, it's going to be 6, and then what is the derivative of x? Just 1, right? I know the 6 is already written there, but the derivative of just x is 1. And then multiplied by the original g. Well, in this case, the original g is y, right? And we're treating this as f and g here. Plus, okay, the 6 stays, right? G prime. Now, is there another function acting on y, other than the fact that it was multiplied by 6x? We're taking care of the fact that it's multiplied by 6x by doing the product rule. Is there anything else acting on y? No. So there's no reason for the chain rule here. There's no reason for the chain rule. So it's 6y prime times the original x. Autumn, I need to see your original quiz.
Okay.
There we go. There should be a spot up in the hallway. Yeah. We got to solve this for y prime. You can go ahead and get started if you want.
Wait, that's 6y is. I don't know what happened. Because the x just is 1, but when you find the derivative of a y, it's not. Is it because it's v over dx, not v over dy? I think, yeah, that's trash. That makes sense.
These combination just makes it so confusing.
All right, man, we're back. Maybe not.
I guess we'll try
In the DX.
Okay, so now what we have to do is solve for y prime. I've differentiated both sides of the equation. Now I solve for y prime. What does that mean? That means I get all the y primes to the left side and everything else to the other. For example, I need to subtract the 3x squared over to the other side, but leave 3y squared y prime on the left side. I'm going to subtract the 3x squared over to the other side. And I want to get this 6y prime x over to the other side. So minus 6y prime x is equal to 6y minus 3x squared. I moved the 3x squared to the right side. I moved the 6y prime x over to the left side. What can I do with my y primes on the left side? Factor them out. I want to factor them out. I've got a y prime in both of those terms. So y prime, I gotta be careful. Y prime is equal to 3y squared minus 6x. 6y minus 3x squared. Okay? And now, to get y prime alone, I divide over. So y prime is equal to 6y minus 3x squared over 3y squared minus 6x. And then I would try to reduce that down as much as possible, but the only thing I can do in this case is just divide out of 3. So y prime, I'll just reduce it down. 2y minus, divide out the 3, come on now. 2y minus x squared over y squared minus 2x. I can't reduce down like this x squared over x or the y over y squared. I can't reduce that down because those pieces are being added and subtracted to something else. All right, so there's y prime. Now it asks next, it says, find the tangent at the point 3, 3. So if I go back to my graph and I look at 3, 3, right here, it looks like it, 3, 3, right here, that coordinate right here. So the tangent should look something like this. I'm estimating my y-intercept to be somewhere up there, maybe like at a 6 or something like that. And it looks like it might have like a slope of somewhere around 1, something like that. But let's check. Okay, now to figure out what my slope would be, I know I have point 3, 3, right? So here's part B. I know I have 3, 3. But to figure out what my slope would be, I need to evaluate y prime at 3, 3. See, before when we were using just regular explicitly defined functions, I only really needed my x value to find my slope. Y'all done? Okay, just go ahead and set it right up here. We only needed my x value to solve for my slope. Do I just need my x value? No, I need both of my x and y values to figure out what my slope is. So y prime is going to be equal to 2 times 3 minus 3 squared over 3 squared minus 2 times 3. So that is 6 minus 9 over 9 minus 6, which is negative 3 over 3, which is negative 1, which makes sense because when I look back at this equation, yeah, I said it was going to be a 1, but obviously down and to the right, that's a negative 1. Okay, so I was correct in my estimation that it was going to be a negative 1 of my slope. And now I go ahead and say, okay, y minus 3 is equal to mx minus 3. So y minus 3 is equal to negative x plus 3, and add the 3 over to the other side. Hey, I was pretty good with my estimation there. Plus 6, negative x plus 6. That's the equation of that tangent line at point 3, comma 3, right at the apex of that curl. It does ask me one more question. It says, at what point in the first quadrant is the tangent line horizontal? Now, this is a fun question. When is the tangent line horizontal? Oh, I didn't mean to write that. Okay, sure. When is the tangent line horizontal? Okay, think about it. What is the slope of a horizontal line? 0, right? So when does the tangent line have a slope of 0? Oh, they're asking me for the zeros of my derivative, right? If I'm asking for when the tangent line is going to go flat, I'm asking you, when is the slope going to be 0? When is the slope going to be 0? Well, if y prime is equal to the slope, I'm really asking for this, 2y minus x squared over y squared minus 2x. I want to know when that's going to equal 0. Well, think of this like a rational function. How do you know when a rational function is going to equal 0? It's when the numerator equals 0, right? When the numerator equals 0. 2y minus x squared is going to equal 0. That's when it's going to happen. Or in other words, 2y is equal to x squared. If I solve that for y, that's y is equal to 1/2 x squared, right? If I divide that by 2, it's either x squared over 2 or 1/2 x squared. So when is that going to happen? When is y equal to 1/2 x squared? Well, think back to my original equation. I've got an x to the third plus y to the third is equal to 6xy. That maps all of the points on this line. So if I want to know when y is going to be equal to 1/2 x, I can just set 1/2 x into y. I basically made for myself like a system of equations. Y is equal to 1/2 x and this thing. So let's plug one thing into the other. Again, it was x to the third plus y to the third is equal to 6xy. Plug in y is equal to 1/2 x squared. So x to the third plus 1/2 x squared to the third is equal to 6x times 1/2 x squared. Because now I've created for myself one full equation with only x's in it. So I can solve for x. All I did was just take that 1/2 x squared and plugged it in. So now I solve x to the third plus 1/8 plus 1/8, 1 over 8, x to the sixth, power to power means we multiply, 1/2 to the third is 1/8. And now this is 3x to the third over here. Oh, okay, combine like terms. Move that x to the third over to the other side. So this is 1/8 x to the sixth is equal to 2x to the thirds. 3x to the third minus 1x to the third is 2x to the third. Okay, this is going to get a little fancy here. Divide by x to the third, not too fancy. Okay, 1/8 x to the third is equal to 2. I divide by 1/8, which is the same thing as kind of like multiplying by 8. So x to the third is equal to 16. So x is equal to the cube root of 16. What is the cube root of 16? Cube root of 8 is 2. Cube root of 27 is 3. So somewhere between 2 and 3. No, I just divided it over. What's wrong?
You have, like, right above you have a root that is equals 3x cubed, and then it's suddenly a 2x cubed.
You subtracted the x.
Oh, wait a sec. Oh, whoops. Oh, yeah. You didn't subtract. I'll email Mr. Hudson. Yeah. Tell him I'll email it. Did you catch that now? You good? All right, so it's the cube root of 16, which is math. Oh, I had it right there. The cube root of 16, which is 2.5. We'll round it to 2.5. So whenever the x value is 2.5, that's when I have the tangent being horizontal. Like, okay, now go back to our graph. When is the x value 2.5? Now, does it happen here? Is the tangent horizontal there? No. But is it horizontal there? Yes. At x equaled 2.5, the tangent line went horizontal. Okay. Doesn't happen at every x equaling 2.5, just once there, happening at above that little apex of that curve. Right there. Okay. Well, that was a fun problem. Let's do one more. Sine of x plus y is equal to y squared cosine x. Sine of x plus y is equal to y squared cosine x. Oh, it's not that bad.
Are you sure?
Positive.
Okay.
In my opinion, this one is easier than the last one.
Okay.
Because why do I say that? Because I'm only asking for the derivative. I'm not asking for the full tangent line. I'm not asking any weird questions about where it's going to go horizontal. This is just find y prime. Now, there's some weird things happening in it. Shocker. But it's still not so bad. Okay, so I'm going to find d over dx of sine x plus y and find d over dx of y squared cosine x. Now, when I go to differentiate the left side, this is a chain rule, right? Do you notice how I have x plus y within sine, right? I have x plus y within sine. You can go ahead and put it in the bin over there. Thank you. X plus y within sine. That means I'm going to go to find the derivative of sine. What is the derivative of sine? Cosine. So it's cosine of x plus y times the derivative of the inside. Now, when I go to find the derivative of the inside, what's the derivative of x? 1. What's the derivative of y? Y prime. So this is multiplied by 1 plus y prime. I don't need to do any other chain rule on y because there's nothing else acting on y. Okay? Like if this had been x plus y squared, well then that's a chain rule in and of itself, just taking the y, differentiating the y squared. Okay? And now we differentiate on the right side. What is this telling me that I have to do? Yes on the y squared, but what else? I just wrote a little dot in there. Product rule. Okay, so product rule, this is now my f, and this is now my g. Cosine x is my g. So remember that it's f prime g plus g prime f. Okay, f prime. Taking the derivative of y squared. Okay, because something is acting on y, I have to do the chain rule. 2y, y prime. That's just the derivative of y squared. Times the original g. Plus G prime, what's the derivative of cosine? Negative sine. Times the original f, y. And from here on, it's just algebra. It's just manipulation. So this is, I'm gonna distribute this whole thing in here. This is cosine x plus y prime cosine x plus y. And then I'm gonna make this, I'll put the y prime all the way out in front because it's sometimes easier to read that way. Y prime 2y cosine x. And then I'm just gonna make this minus. Now be careful. This is not sine xy, right? Be careful with that. That's y times sine of x. Be careful with your notation there. If you said sine xy, that might tempt you to say that it's the sine of x times y, which is not true. It's the sine of x, dramatic pause, times y. And that one, oh, good catch. Oh, good catch there. Yeah, because my original f was y squared, not just y. Superstar, as Mrs. Simone would say. All right, so now let's bring all the y primes to the left side. So I've got this one, y prime cosine x plus y. I'm going to subtract over this other y prime, minus y prime 2y cosine x. I'm going to subtract over the cosine x plus y. Minus this y squared sine x. Or does it really matter there? If you wanted to say negative y squared sine x minus cosine x plus y, that's fine too. Okay, now look over here. Both of those terms have a y prime in it. So y prime gets pulled all the way out. Cosine x plus y minus 2y cosine x. Right side stays the same. Negative cosine x plus y minus y squared sine x. And now I divide over y prime is equal to negative cosine x plus y minus y squared sine x over cosine x plus y minus 2y cosine x. Yeah. Now let's find the equation of the tangent line. Just kidding. Didn't I say this properly?
Yeah. That's like, I don't know, Mr. Alec. That looks like hieroglyphics to me. I'm not sure that's math.
You know the cool part about that? That's the graph.
How do you figure that out? In some ancient time, figured that is equal to that.
I know.
That's a lot more letters. It doesn't look like math.
I really want to know.
It's a lot more letters than math.
You know what's really cool? And now this is not part of the notes. This is just like me nerding out a little bit. So many, this is the first time we really talked about what it means to be an implicit function. But like the book gave this diagram. Look at all these cool implicit functions there are. Like look at that one. X squared minus 1 times x squared minus 4 times x squared minus 9. Something weird going on with the difference of squares. Times y squared times y, or is equal to y squared times y squared minus 4 times y squared minus 9. That's the function that it makes?
That's not a function.
No, thank you. That's the graph that it makes, right? Like, look at this one. Okay, I'm gonna do this. Indulge me here. Okay, so this is cosine x minus sine y is equal to sine y minus sine x. What? What?
In the world? Whoa.
Weird.
That's interesting. Imagine you like do an equation.
What?
To like solve two.
I like that.
And how you just find your answer.
Yeah. It's like, find when the slope is. Yeah. Y'all done.
Yeah. I like your art.
Thank you very much.
How do you
Just
figure that out?
straight up hard attack.
It's intimate. I wouldn't say small. Intimate.
Intimate. Okay.
How do you figure that out?
I don't know. I don't even know. That's like beyond me.
This man looks like
Like,
some
what
numbers
do you
you
use
go.
that?
Yep.
What do you use that graph for?
I don't know. Yeah, that's when somebody says like, okay, when am I going to use this in real life? I say,
Actually,
When am I
will
gonna
I
use this
ever
in
need this?
Anything ever.
Will I need like a picket, like a?
where did the other? Oh, there it is. Sine xy. Yep. Sine xy is equal to sine x plus sine y. Whoa!
Ooh, that's something.
Looks like how you
Yeah, that's just like some.
That's kind of how calculus goes in my brain.
Right, yeah.
Confusing.
You know what that looks like? Just scribbles. That's what that looks like.
This equation contains line physiology.
Right.
Oh boy.
See?
Some of the tissues are like scribbles.
Right?
Why?
Math imitating life or life imitating math?
Don't get that. What even is my life? I wore this. Which came first.
Chicken or the egg? I've got to do this one. X squared. Okay. X. Oh yeah. Minus 1. X squared minus 4. X squared minus 9 equals Control C.
Who won the first Super Bowl ever? Packers.
Oh.
See, I didn't put that. I missed that one.
Green Bay Packers. Bart Starr was the quarterback for that team. You know, I'm a wealth of stupid knowledge.
I wouldn't say you're a lot of stupid knowledge considering you're going to be coaching back in a challenge.
Yeah, that's true.
What are you making? Where do these functions come from?
I'm just copying this.
Like the functions you're creating.
What?
Why?
So cool though.
It's like Batman or something, you know?
It's symmetrical.
I will.
Yeah.
Mathematical magic.
This is an even function.
Question: why are they called implicit functions if it's not a function?
They're called implicit equations.
Equations and why?
Got him.
So weird.
Why? Why do these need to exist in the first place? That's the
What even
overall
is math
question.
anymore?
Why?
Right. Honestly, like, who invented math?
Like, what is
You know
it?
what's funny?
Numbers?
So, like, our number system is called the Arabic number system because all of our numbers come from like northern Africa, like Egypt. Like that's like where our numbers come from. They're called like the Hindu Arabic numeral system, like not the Roman numeral system, the Hindu Arabic numeral system. And like if you pulled, this is hilarious, but like if you pulled like across the U.S., should we be teaching Arabic numbers in schools? Like 60% will say no.
They have no idea.
They have no idea what you're talking about.
That's actually funny.
All right, let
I
me.
would probably, if I saw that question, I'd be like, no.
No.
I would not.